#2 session. Today we are going to discuss a gas refrigeration cycle, its working principle, the processes involved, application and its advantages. And we have to start the second topic, which will be on absorption refrigeration. We will start it today, and maybe in the next lecture we'll finish it. So let's start with the gas refrigeration cycle. It is a relatively simple cycle. So this is the sketch of the gas refrigeration cycle right here. It's consisting of a compressor, a heat exchanger, a turbine, and then a heat exchanger. So basically it is consisting of 2 heat exchangers. And this is the TS diagram, the process diagram of the gas refrigeration cycle, which is based on the reverse Brayton cycle. There is no phase change involved in this cycle, as this is a gas, so these two temperatures are in the gas phase. There is the vapor dome is not here. Basically, that's what it is. So there is no phase change process. Therefore, no latent heat is involved. Only sensible heat is involved. Sensible heating and sensible cooling is involved. Just sensible heat is used. Also, mass flow rate has to be high because we are not using latent heat. So to get the same kind of cooling effect, we have to have the higher mass flow rate. So higher mass flow rate is involved here. As we know that the Carnot cycle, which is the standard cycle for all comparison, and the reverse Carnot cycle, which is the standard comparison for the refrigeration cycle, are identical, except they are reversed. The reverse Carnot cycle operates in the reverse direction. So the forward Carnot cycle is for heat engine, and if we reverse it, we get the reverse Carnot cycle, which is used in the refrigeration cycle. So similarly here also the Brayton cycle is the power cycle, gas power cycle, and if we reverse it, we should be getting our refrigeration cycle, and that refrigeration cycle is the gas refrigeration cycle. In fact, we can say that the vapor compression cycle is essentially a modified Rankine cycle operating in the reverse direction. Similarly here, the reverse Brayton cycle becomes the gas refrigeration cycle. So the process 1 to 2 is the isentropic compression of gas accompanied with a rise in temperature. So we get the air or the gas at state 1, pressure 1 and temperature 1, and then we compress it. So as we are compressing, its pressure is rising and its temperature is rising, so it comes to state 2, from compressor to state 2. Inlet of the compressor compressed to outlet of the compressor, which is state 2. And then from 2 to 3 it is the heat rejection into the environment, QH, and then 3 to 4 is the expansion process in the turbine. We are not using a throttling valve here. Instead we have an expander, or you can say that a turbine instead of a throttling valve. In gas refrigeration cycle we use a turbine to expand the air. As a result of that, its pressure will drop and its temperature will drop, and then as that is 3 to 4 process. 3 to 4 is isentropic expansion in turbine, during which gas temperature drops. So 1 to 2 is the isentropic compression in the compressor. 2 to 3 is the isobaric cooling of the high temperature. Make note of this isobaric. In the vapor compression system we have isothermal process, but here it is isobaric cooling of the high pressure. Isobaric cooling of the high pressure, high temperature gas. 3 to 4 is the isentropic expansion in the turbine, during which gas temperature drops, and 4 to 1 is the cool gas absorbs heat from the refrigerated space. So this 4 to 1 is the cooling effect produced, refrigerating effect produced, but this is also not latent. Instead, it's all involves is sensible heat will be absorbed by the air or by the gas. So this is the 4 process of a gas refrigeration cycle. So the next slide will show you a comparison between the gas power cycle, the Brayton cycle. This is the sketch of the Brayton cycle, and This is the sketch of the Brayton cycle, and this is the process diagram of the Brayton cycle, this one. So if we reverse it here, the flow is going in the clockwise direction, 1 to 2 in the compressor, 2 to 3 in the heat exchanger, 3 to 4 in the turbine, and then 4 to 1 in the heat exchanger again. So that's how the Brayton cycle is, gas power cycle is, and the 1 to 2 is the compression, okay, 2 to 3, 3 to 4, and 4 to 1. So it's clockwise direction. And in the gas refrigeration cycle, the cycle is reversed, so it goes in the anti-clockwise direction. So it is 1 to 2 is in the compressor, then in the heat exchanger, then expanding in the turbine, and then 4 to 1 is the evaporator in the evaporator process, you can say that. So that is 4 to 1. So two cycle. I'm showing you the 2 cycle here and the 2 sketches here, just to get an idea. So like in the gas power cycle, the compression is supposed to be isentropic and expansion is isentropic. Same here, the compression is isentropic and the expansion is isentropic, but the other 2 process is isobaric process. Okay, now moving on. The COP of the gas refrigeration cycle is COPR is QL. QL is the desired output divided by the W net in. So here we have a turbine and a compressor. So the net work. So the net work will be compressor work, which will be higher, minus the turbine work. So here turbine is basically helping to run the compressor. So there will be compressor work will be reduced by the turbine work. Turbine will share in the work of the compressor. If it's ideal cycle, then the COPR can also be shown to be T4 divided by T3 minus T4, where QL is H1 minus H4 from the diagram. If you look it up, the QL is H1 minus H4, and W compressor is H2 minus H1, and W turbine is H3 minus H4. So compressor work is H2 minus H1, the turbine work is H3 minus H4. And the part of the compressor, whatever turbine work is produced, it is being used to run the compressor. So the compressor work required will be reduced. Okay, so moving on. Where was I? Okay, there you go. The actual cycle differs due to non-isentropic compression and expansion process. So this is the ideal process, ideal compression process, and ideal expansion process. In actuality, the compression process will not be ideal. It will be, and the actual process will deviate. It will deviate in the sense that its entropy will increase. So from 1 to 2, if its entropy increases, it will go in this fashion, and the compression process will be like here. Okay, and when it is expanding, it will not be an isentropic process, so the entropy will increase and it will come like this. So overall, the cooling effect produced will be reduced in the actual cycle as compared to the ideal cycle. Okay, and moving on. Okay. So the actual cycle differs due to non-isentropic compression and expansion process. And number 2, the pressure drops in the heat exchangers. We are considering constant isobaric process, but there will be pressure drop in the heat exchangers, both in the condenser and in the evaporator. COP is much lower compared to the vapor compression cycle. COP in the gas refrigeration cycle deviates from the reverse Carnot cycle because the heat transfer processes are not isothermal. In fact, the gas temperature varies considerably during heat transfer process. Consequently, the gas refrigeration cycle have lower COPs relative to the vapor compression refrigeration cycle or the reverse Carnot cycle, because it is working on the sensible heat. So that's why its COP will not be as high as the vapor compression process. It will be always lower. the range of COP for gas refrigeration cycle is like around 0.4, while the vapor compression refrigeration cycle COP is about 3.5 or higher. So you can see that that's why COP is not much higher. It has a low COP. The gas refrigeration cycle have lower COPs relative to the vapor compression refrigeration cycle or the reverse Carnot cycle. So application of gas refrigeration cycle, where it is being used. So normally the gas refrigeration cycle is used in the aircraft because of its lightweight. Despite their relatively low COP, the gas refrigeration cycle have two desirable characteristics. They involve simple, lighter components, which makes them suitable for aircraft cooling, and they can incorporate regeneration, which makes them suitable for liquefaction of gases and cryogenic applications. So this cycle can be easily converted into a regeneration cycle, and you can keep lowering the temperature of the air so that it reaches the cryogenic temperature. So it can be used in liquefaction of the gases. The other advantage is that you don't need an extra compressor. It can use the same compressor which is used in the aircraft engine. So that's why it becomes lighter. Aircraft cooling system. Okay, even though the outside temperatures are very low at high altitudes, still cooling is required, because your airplane is flying at the altitude of 10 km or above, okay, in the stratosphere, above the troposphere or close to the troposphere it is flying. So the temperature and pressure there is very low. Normally the temperature is in the negative range, and the pressure is could be as low as 0.15 bar or 0.2 bar compared to the standard atmospheric pressure. So it has low pressure and low temperature, but when this low temperature or low pressure air, which is moving at a very high speed, because the aircraft is moving about at a very high speed, so when it comes and touches the aircraft surface, its temperature and its pressure rises. Large internal heat generation due to occupants, equipment, etc. in the aircraft. Why do we need the refrigeration in the aircraft while it is moving in such a high altitude and it has very low pressure and low temperature? Still we need to supply the aircraft with the cooling system. Why? Because the heat generated from the occupant and the equipment, heat generation due to skin friction caused by the fast moving aircraft. As this aircraft is moving in a colder temperature, but still as the air starts touching the surface of the skin of the aircraft, its temperature, pressure both rises. So that's why. At high altitudes, pressurizing the outside air to cabin pressure leads to a larger temperature rise. We are getting, because this is a air refrigeration system or gas refrigeration system. So where is this gas we are getting it? The air we are getting it from the outside, and then we need to compress it. It is 0.15 bar. It is coming at 0.2 bar, it says here, and we have to compress it close to 1 bar, which is atmospheric. 0.8 bar we have to. So when you compress it to up to that much, its temperature will rise. So at high altitude, the pressurizing the outside air to cabin pressure leads to a large temperature rise. For example, at 10 km altitude, air is at around 0.2 bar and 223 Kelvin. So very low temperature, negative temperature. Okay, compressing it to 0.8 bar increases its temperature to 332. So it becomes very high. And the solar radiation. So these are the reason that increases the aircraft's temperature or heat inside the airplane. That's why we need to provide cooling system in the aircraft. Okay. So advantages of gas refrigeration cycle for airplane refrigeration. Why do we use gas refrigeration cycle or air refrigeration cycle in the airplane instead of a vapor compression cycle? Okay, so the gas refrigeration cycle is considered most suitable for aircraft cooling because air is cheap, safe, non-toxic and non-flammable. So if you use air as a refrigerant, these are the advantages of that. Leakage of the air is not a problem, so it will not cause any poison or anything, or any kind of rusting or anything. So that's why it is safe. So we can use air as a refrigerant. Cold air can directly be used for cooling. So instead of passing this air into a pipe and then blowing air on top of it, as we do normally in our vapor compression refrigeration evaporator system, here we simply expand it, the air's temperature drop, and then we send it to the cabin directly, and then we get fresh air from the outside again, from the compressor of the engine again, and then so that's how it works. So we don't need to recycle the air again and again as we do the recycling of the refrigerant. So low temperature heat exchanger is not required, that is saving in the weight. We don't have the evaporator actually, we are just passing the cold air into the cabin. As much air is required, that's the quantity of air which will be supplied. Separate compressor for cooling system is not required. As I said, the aircraft engine has a compressor, so we actually take this air or bleed this air from that compressor, which further reduces the weight. Okay, what are the disadvantages? The disadvantage is the gas refrigeration cycle has a low COP value, as I said, because it is not working on the latent heat, it is working on the sensible heat. So its COP value is reduced. It has COP value of 0.4 as compared to the COP of the vapor compression refrigeration cycle, which is about 3.5. Because of this, it is not used for domestic refrigeration. Also, it needs sensible heating. As I said, the whole entire process is outside the vapor dome in the superheating region. So there is no use of latent heat. Only sensible heat is required. So that's why we cannot use it in the domestic application, but we can use it in the aircraft. Next screen is the refrigerating process in the aircraft. Simple air refrigeration cycle for the aircraft. How does it work? So as you can see, air outside air is coming at point 0, which is at low pressure of 0.15 and very low temperature. But when it enters into the aircraft engine, its pressure and its temperature rises. So it goes from 1.5 to somewhere around 1 bar maybe. Okay, so we are getting from ambient condition. This line is showing the ambient at point 0. So at point 0 we are getting 0.15 bar air at low temperature, and when it enters into your aircraft engine, it becomes at this state 1. Okay, 1 bar, which is about approximately 1 bar. Okay, and then it will be compressed. After it's compressed at state 2, we bleed it from the engine compressor, and then we send it to a heat exchanger. The yellow one is the heat exchanger, and because after compression the air has gone higher in the temperature. As you can see, the air temperature will rise from 1 to 2 after the compression. So 2 to 3, it is being cooled at the same pressure. So the cooling process occurs in the heat exchanger. This is the yellow one is the heat exchanger, and in the yellow one we have our compressed hot air in the pipe, and we are bleeding another amount of outside ambient air which is at lower temperature before the compressor. So we're bleeding that one into this heat exchanger, and so this cold air will cool down the compressed air, and then it will go into the expander, which is the turbine. In the turbine, its temperature will drop, and this drop low temperature air will descend into the passenger cabin. So there is no evaporator here, as you can see, and the air that we had bled from the engine after doing the heat exchange process will pass through this fan. So it will rotate this fan, that will create a vacuum here, and this air which is coming after the and which will this will move the fan. The turbine is also moving the fan, So there will be vacuum generated here, so that will push this air, which is we are using it in the heat exchanger, to go outside the aircraft. So that's the mechanism of a simple air refrigeration cycle in an aircraft. I just wanted to give you an example how does it work in the aircraft. So the main application of gas refrigeration cycle is in the aircraft or in the liquefaction process, cryogenic process, regenerative cycle. I didn't show you the regenerative cycle, but it is available in your book, so you can go over it. So this is all that I have for the gas refrigeration cycle. So if you have any question on it, you can ask me and I'll try to clarify during our live session. And next I want to talk about the vapor absorption. That is our last refrigeration cycle that I want to discuss. So absorption refrigeration system. So it is different than the vapor compression refrigeration cycle in a major way, is that we are replacing the compressor by 3 other components. So there is no longer compressor. Instead of a compressor, we are using a pump. So the 3 items which is replacing your compressor is that absorb vapor in the liquid while removing heat, elevate pressure of the liquid with the pump, release vapor by applying heat. So the compressor is replaced by these 3 items. I will show it one by one. So another form of refrigeration that becomes economically attractive when there is a source of inexpensive thermal energy at a temperature of 100 to 200 degrees centigrade is the absorption refrigeration system. So normally you will not try to use absorption refrigeration system unless and until you have waste heat, some kind of waste heat available, or inexpensive heat available, either with the solar system, you are getting heat from the solar system, or you are having a gas turbine engine which is exhausting hot air at 400 degrees centigrade. Then you try to use that one in your vapor absorption refrigeration. Some examples of inexpensive thermal energy source include geothermal energy, solar energy, and waste heat from cogeneration or process steam plants, and even natural gas when it is available at a very low price. So it is only viable when you have a cheap source of thermal energy available to you. The absorption cycle is similar in certain respects to vapor compression cycle. A refrigeration cycle will operate with the condenser, expansion valve, and evaporator. So those 3 items are still here. Condenser, evaporator, and expansion valve is still here. But what is not here is these 3 items are same as we had in the vapor compression refrigeration cycle. So what is not here is the compressor, and compressor is being removed by 3 other devices. One of them is the pump, the other one is the generator, and a heat source. So moving on, the vapor compression system uses a compressor for this task. The absorption system first absorbs the low pressure vapor in an appropriate absorbing liquid. Embedded in the absorption process is the conversion of vapor into the liquid. Since this process is akin to condensation, heat must be rejected during this process. The next step is to elevate pressure of the liquid with a pump. Third step is, and the final step, releases vapor from the absorbing liquid by adding heat. The amount of work required by absorption cycle to drive the pump is very small as compared to the work needed in the vapor compression cycle. The energy required to release the vapor from the absorbing medium is the main cost of the system. So when your absorber has absorbed your salt, then to release it back, I'll show you the process how it does it. You have to supply the heat energy. So supplying that heat energy is the actual cost of this vapor absorption system, is the actual operating cost. which is called generator. In the generator you have to supply the heat. So you have a absorber, a generator, and a pump. That is what replacing your compressor. Absorber, pump, and release vapor. So that is the generator, release vapor by applying heat that we do in the generator. I'll show you the diagram, the sketch of the system, then you'll see it there. So the two most widely used system are as opposed to the refrigerant that we use in vapor compression refrigeration system. The refrigerant used here is not one, it is two. It has a primary refrigerant and a secondary refrigerant. So here the two systems we have is one we call ammonia water system. Ammonia is the refrigerant and water is the transport medium. Okay, and the other one is the water lithium bromide system. Water is the refrigerant and lithium bromide is the transport medium. Okay. So in the lithium bromide water system and aqua ammonia system, if we do a comparison between these two, so lithium bromide water system, water is the refrigerant and lithium bromide is the transport medium, and here ammonia is the in the ammonia water system, ammonia is the refrigerant and water is the transport medium. So when water is in lithium bromide, when water is a transport medium, then water is non-toxic working fluid. Ammonia is toxic and reacts with the copper. Comparatively lower system cost for lithium bromide. For aqua ammonia has higher cost because it has an extra analyzer type of equipment that you have to install to separate the ammonia from the water. So that's why it becomes a little bit more costlier as compared to lithium bromide and water system. Lithium bromide is non-volatile, which requires a simpler system. System requires additional components due to high volatility of the ammonia and water. So it has the lithium bromide has higher COP, while aqua ammonia system has lower COP, relatively low COP. Limited to the application where the minimum temperature is greater than 0 degree, because water is acting as a refrigerant here in the lithium bromide water system, so you cannot go below 0 degree. Normally it goes as low as 7 degree maybe, or maybe 3 or 4 degree, but not, it cannot touch 0 degree, because at 0 degree the water will freeze, so you cannot go that low. But in case of ammonia you can achieve sub-zero temperature. Low temperature can be achieved in aqua ammonia system. System operates below P atmosphere, system pressure is above P atmosphere. Here we can afford to go below atmosphere, but here we cannot, because it has to operate above atmospheric pressure. Because of the ammonia cannot operate with below ATM pressure. So moving on, vapor absorption system compared to vapor compression system. A liquid is compressed instead of a vapor. So here the compression process we are using a pump. So the pressure we are rising using a pump. So we are basically pressurizing a liquid, not a vapor. Thus the work input is very small, less than 1% of the heat supplied to the generator. Okay. So the pump work is very small as compared to the compressor work in the vapor absorption system. Can be used to furnish heating and cooling simultaneously. Much more expensive. It's a bulky, heavier system, large system, so that's why it is expensive. More complex and occupy more space. It's a larger system. Much less efficient. COP of the system is less than 1 as compared to COP of the vapor compression refrigeration system. On that one, as I just told you, that it goes as high as 3.5, but here it will be always less than 1, requiring much larger cooling towers. More difficult to service since they are less common. Should be considered only when the unit cost of the thermal energy is low and is projected to remain low relative to electricity. primarily used in large commercial and industrial installations. So normally in your vapor compression refrigeration system is available from 1 ton and 1.5 ton and 2 ton and 3 ton and 4 ton. But if you are installing a vapor absorption system, it has to be starting from like 10 tons or 20 tons or so. So these are larger system, bulkier system. That's why they are costlier and only used by the commercial or industrial application. It is not used for domestic purpose. Okay. So what is the principle of operation? How does it produce cooling effect? How does it work? So the working fluid in an absorption refrigeration is a binary solution consisting of refrigerant and absorbent, as we discussed, water ammonia system or lithium bromide water system. So one of them is the absorbent and one of them is the transporter. Okay. So in figure 1a, two evacuated vessels are connected to each other. So let's say these are the two vessels and they are evacuated. There is vacuum in them and they are being connected with each other. The left vessel contains liquid refrigerant while the right vessel contains a binary solution of absorbent refrigerant. So the left one contains liquid refrigerant. So left one, let's say this one has the water and this one has the lithium bromide solution into it. Okay, and this is just the water. Water is the refrigerant. Okay, in the lithium bromide and water solution. Let's consider that one. So what will happen? This lithium bromide salt has an affinity for water vapor. It attracts water vapor. So what will happen here is that it will, when the pressure is same, we said it's evacuated, so we are making the pressure same first, and then as soon as we connect the two, what will happen? This lithium bromide solution, which has an affinity for water vapor, will attract water vapor from here and it will start coming here. So this salt will be changing into solution. Okay, slowly it will become solution and the refrigerant will be moving out from here. When the water vapor leaves from here, what will happen to this vessel? If the water vapor moves out from here and it goes into the bromide salt, lithium bromide salt, then what will happen? That there will be a low pressure will create. So more water vapor will try to escape from here. Hence the temperature of this vessel will reduce. That's the refrigerating effect produced. Okay. Now to separate this, we want this process to keep on going, but it will not keep on going. It will go up to the certain point when it becomes the lithium bromide salt becomes saturated with the water, then there will be no more process. Then unless and until we can remove some more water from here from the solution, the process cannot go on. So we need a mechanism to reverse the process. So the reverse process is we supply heat to this solution in this figure here. We are supplying heat to the solution in the next process. As a result, the water and the salt will get separated. Water will go back into the refrigerant. Okay. And if we can somehow combine these two processes together, then this cooling effect will keep on going. It will become a refrigerating system. So in figure 1a and 1b, these are the two figures that we are talking about. 1a, two evacuated vessels are connected to each other. The left vessel contains liquid refrigerant while the right vessel contains a binary solution of the absorbent refrigerant. Okay, so this has a water and lithium bromide solution. The solution in the right vessel will absorb refrigerant vapor from the left vessel, causing pressure to reduce. So it will absorb more and more and its pressure will drop. While the refrigerant vapor is being absorbed, the temperature of the remaining refrigerant will reduce. So here we will have a reduced temperature. As a result of its vaporization, this causes a refrigerating effect to occur inside the left vessel. Inside here in the left vessel it will occur. Now how to reverse this process? If you want to keep on continue, it will become saturated and it will not go, the process will not continue. So we need to reverse it so that this can keep on going. So at the same time, solution inside the right vessel becomes more dilute because of the higher content of the refrigerant absorbed. This is called the absorption process. This is the absorption process. So A is the absorption process occurs in the right vessel, causing cooling effect in the other. right vessel is absorbing it and left vessel is producing the cooling effect. B. Refrigerant separation process occurs in the right vessel. Here the refrigerant separation process is occurring right vessel as a result of additional heat from the outside heat source. So here we will supply our heat in this right vessel. We will supply the heat from the low temperature heat source like solar or waste heat that we have. We'll supply it here and we'll separate it. Now we need to connect these two process. So next screen will show you that this is what we did. We connected those 4 vessels together. Now the process can keep on going. Normally the absorption process is an exothermic process. Therefore it must reject heat out to the surrounding in order to maintain its absorption capability. Whenever the solution cannot continue with the absorption process because of the saturation of the refrigerant must be separated out from the diluted solution. So this is the absorber, okay, and this is the evaporator. The cooling effect is being produced here, and water vapor is being absorbed here in the solution, okay. So then what do? We send this solution using this pump into the generator. The generator, we are supplying the heat. We are supplying outside heat into the generator. As a result of that, it will separate it, and the refrigerant will come out of it, and refrigerant will go into the condenser, and the high concentration solvent will come out here into the absorber, back into the absorber. High concentration solution, you can say, because some of the water is already left, so the solution has higher concentration here, and that will come back here. And this is the valve which will keep the pressure difference between the two. This is the pump which is creating the pressure difference between absorber and the generator. Normally the absorption process is an exothermic process. So here some heat will be rejected. This is the amount of heat which is being rejected. Therefore it must reject heat to the surrounding in order to maintain its absorption capability. Whenever the solution cannot continue with the absorption process because of the saturation of the refrigerant must be separated out of the diluted solution. So this diluted solution will be pumped up into the generator, and heat will be supplied into the generator so that it can separate your refrigerant and your absorber. Heat is normally the key for this separation process. It is applied to the right vessel in order to dry the refrigerant from the solution, as shown in figure 1b. So 1b was the other figure on the other side, this figure. When we supply heat, it will separate the refrigerant from it and send it back here. The refrigerant vapor will be considered by transferring heat to the surroundings. With this process, the refrigeration effect can be produced by using heat energy. However, the cooling effect cannot be produced continuously unless the process cannot be done simultaneously. Therefore, an absorption refrigeration cycle is a combination of these two processes as shown in figure 2. So these two vessels, these two processes, we combine it together in this fashion. So then it becomes a vapor absorption refrigeration system. The absorption cycle. So I'm going to start from here in the next lecture, and then we will look at some of the application of it, and then how to do the calculation for this process. So I would like to stop right here, where I have explained you how the cooling or refrigeration is being produced into the vapor in the vapor refrigeration system. Then next we will start with this vapor in the absorption cycle, and we will do its application and its advantages, and we will do the COP and other calculations, etc. for it. So if you have any questions, if you could not understand anything, you can mark down the slide number and ask me during your live session. Thank you. I thank you very much again, and we'll meet inshallah again in the next lecture. Thank you.